Hey, welcome back to chemistry. And so with this presentation, I want to talk about something called electron configuration, which tells you that for any particular element, which orbitals of that element have electrons. For example, does the element let's say it's vanadium. Will its 1s orbital have electrons? Will its 3d orbital have electrons? Will its 2p orbital will have electrons? So you have to figure out for any particular element which orbitals are filled up with electrons. And so I sort of need to teach you how to do that. And so the first thing you need to learn is you have to understand the order of the orbitals that are filled by electrons. And so the basic rule here is remember that orbitals are filled up from lowest energy to highest energy. So the first electrons which go into an atom will go into the lowest energy orbital, say like the 1s orbital is the lowest energy orbital. And then once the 1s orbital is filled, then the next higher energy orbital up, the 2s is filled, and then the 2p and the 3s and the 3p and so on. Now, here's the thing. You can memorize that order of orbitals if you want to, or there's a quick way to figure out the order because it may not be so clear sometimes what the order of the orbitals is. And so the way you figure out the order of the orbitals is using something called the diagonal rule. So I think the best thing for me to do is just to sort of draw out the diagonal rule on this board here, and then that will tell us what the order of orbitals is that electrons fill from lowest energy to highest energy. So what you do is you list out all the orbitals that an element can have. So for example, all elements can have a 1s orbital. So a question I ask is, can an element have a 1p orbital? And the answer is no. And so you might remember when you're dealing with the first energy level, the only sublevel that exists is the s sublevel. There is no p sublevel. So I do not write 1p here. Now, in the second energy level, there is a 2s sublevel. There's also a 2p sublevel, but is there a 2d sublevel? And I think you know by now, when you're in the second energy level, the only two sublevels that are there are the s sublevel and the p sublevel. There is no d sublevel. Third energy level, it's 3s, 3p, 3d. There's no 3f. 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. Now you might have learned somewhere that after the f sublevel, you might have another higher energy sublevel called the G sublevel. So the question is, do we write it in 5G? Now you could if you want to. I usually leave it out. I don't go any further than F, and the reason is if you look at the periodic table, I think you have now up to what? I don't know, about 118 electrons that can fill orbitals. And so I think by the time you get up to the 5G, that 5G will not pick up those highest energy level electrons of the 118 that are there. So I don't bother writing 5G. So I next write 6s, 6p, 6d, 6f, 7s, 7p, 7d, 7f. And so that should be enough. Okay. So to figure out the order of the orbitals, what you have to do is draw diagonal lines to this sort of chart here. And so the first diagonal line only cuts through the 1s orbital like this. And so I'm going to put a 1 here for that. The second diagonal line only cuts through the 2s like this. The third diagonal line cuts through the 2p and 3s. The fourth diagonal line cuts through the 3p and 4s. The fifth diagonal line cuts through the 3d, 4p, and 5s. And so on, 4d, 5p, 6s for the sixth diagonal line, and then 4f, 5d, 6p, 7s. So you can write out the order of the orbitals determined by going through these diagonals in sequential order and just writing out the orbitals that they hit in order. So the first diagonal line hits 1s. So the first orbital that is filled is the 1s orbital for any atom, and that will have the lowest energy. So we're done with the first diagonal. Going down to the second diagonal, it hits only 2s. So that is the next orbital up in terms of energy. Third diagonal is 2p3s. and then go to the fourth diagonal, it's 3p, and then notice it's not 3d. You go to the fourth diagonal, it's 3p 4s. So 4s actually has a little bit lower energy than 3d. So it's 3d 4s, or excuse me, 3p 4s. 3p 4s. Okay, now we go to the fifth diagonal, and we have 3d 4p 5s. So it's 3d 4p 5s, and then the sixth diagonal, which is 4d 5p 6s. So it's 4d, there we go, 5p 6s. And so you can keep going on with this, but again, sort of to know that this order, which I'm writing out from left to right, is the order of orbitals in terms of energy and also the order in which they are filled. So here again, on the left side, the 1s orbital is filled first, then this 2s orbital, then the 2p, 3s, 3p, 4s, etc. Okay, so we have that order there. I might leave that there just for a second. So I'm just going to erase this chart here. Now, I think it's kind of a good idea to have in your mind sort of a sense of what the energy diagram of these orbitals on that diagram would look like. So what I'm going to do is I'm going to draw an axis here. This is going to be a y-axis, and I'm going to put energy on the y-axis. And I'm going to indicate on this diagram where the orbitals reside on this energy diagram. And so the lowest energy orbital on this axis is going to be as low as I can possibly place it. So I'm going to put it here for now. So I'm going to put 1s here. So to indicate that I have an orbital, I have a line here. How about the 2s orbital? Well, it's higher in energy, so I'm going to put that a little bit further up here. So that'll be the next orbital that is filled. And then next is 2p. That's going to have a little higher energy than 2s. I could put the 2p right above the 2s, but just, so it's a little bit clear, I'm just going to shove it over to the right here. So I'm going to write a 2p orbital here, but here's the thing. You might recall that the s sublevels of the 1 and the second energy level only have one orbital. So that's why I drew one line there. But a p sublevel, doesn't matter what energy level belongs to, it could be the second, the third, fourth, whatever. A p sublevel has 3 orbitals. And so what I'm going to do is I'm going to draw 3 lines here. So 1, 2, 3 are the 3 orbitals for the 2p sublevel. Okay, so what's the next orbital up? So this is the third energy level s sublevel, so that's 1 orbital. So I'm going to put this here. So one of the things I want you to notice as I'm drawing in these orbitals, I'm kind of squeezing them closer and closer together, because that's what has been experimentally found, is that as you go further up in energy, the orbitals are not, or have less and less of an energy difference as you go up. So we have the 3s there. The next is the 3p. So a little bit higher energy than that. I'll put this in the p area here. There are 3 of them, orbitals, because it's p. Okay, so what's the next one is the 4s, which is a little bit higher than 3p. And then the next one up is the 3d. That actually has a little bit higher energy than 4s. So I'll just put that over there. So would I write out 3 lines for 3 orbitals for the 3d sublevel? No, because this is d sublevel, there are 5 orbitals, and so I have to draw out 5 lines. And so I'm just going to go a little higher than the 4s and draw out 5 lines. 1, 2, 3, 4, 5, and this is the 3d sublevel. And if you wanted to, you can go up further from there. Now, one thing I want you to notice is that when we have a sublevel with multiple orbitals, whether it be a p sublevel or a d sublevel, what I tried to do was each of these orbitals, I tried to put them on the same line, indicating that each of these orbitals in the sublevel have exactly the same energy. So when you have orbitals in a sublevel that have exactly the same energy, they are said to be degenerate orbitals. And so the word is degenerate, D-E-G-E-N-E-R-A-T. So also the 3d orbitals are degenerate orbitals because these 5 orbitals of the 3d sublevel have exactly the same energy. And so these would be degenerate orbitals as well. Okay. So what I'm going to do now is I'm going to carry out a bunch of electron configurations. And so I'm going to erase this briefly, and I'm going to make a new chart. Okay. So I'm going to write up here, in this corner here, I'm going to write element and electron number. Let me pop the slide over. So here is another picture of the energy levels for each of these sublevels. And so I want to go to here. I'll talk about what's on the slide in just a second. So back to this chart here that I'm drawing out is element electron number. The next thing I want to write is orbital notation. And then I want to write electron configuration notation. Then I'm going to write Qn for quantum numbers. Then I'm going to write something called Lewis dot. I'll explain what that means in a minute. And then I'm going to write the abbreviations P or D. Okay, so P means paramagnetic, and D means diamagnetic. Diamagnetic. Looks like I spelled it right. Amazing. Okay, so I'm going to put little lines here. Okay. All right. And so as I'm going through the electron configurations for some of the elements with the fewest number of electrons, I'm going to be describing it as I go along, and I'll be using some vocabulary. And I'll try to define the vocabulary as I'm going through this. But if you want, you can sort of refer to the glossary I have on this board here. Okay, or on the slide there. Okay, so the first thing I want to do is consider the electron configuration of hydrogen, which has only one electron. So I have hydrogen here, and there's one electron, so I'll put parentheses 1e. So the question is, what orbital does this one electron of hydrogen go to? So in hydrogen, there are plenty of orbitals. There is the 1s, the 2s, the 2p, 3s, 3p. Which one does it go to? Well, what you know is that electrons go to the lowest energy orbitals that are available to them, and they fill those orbitals. And so the lowest energy orbital that's available to this single electron from hydrogen is a 1s orbital. So this single electron from hydrogen will go there. So to indicate we have a 1s orbital in hydrogen with a single electron, this is what I do, how I write this out in orbital notation. I draw a line in orbital notation to indicate the orbital, and then I write 1s here. And to indicate the electron, I draw a line with an upward arrow. So this is the correct orbital notation for hydrogen's single electron. So there's also something called electron configuration notation. So this will also indicate that there is one electron in the 1s orbital of hydrogen, but I use numbers and letters and superscripts to indicate that. So we have one electron in the 1s, so I write 1s, and to indicate the number of electrons in that 1s orbital, I write a superscript 1 like this, and so this is the electron configuration notation for the hydrogen electron. Okay, so one thing you have to sort of continue to suffer through is figuring out what the quantum numbers are for this electron. So let's see if we can figure that out. So you might remember there are 4 quantum numbers, so I'm going to list them here. There is the quantum number n, which indicates the energy level that this electron is in. There's the quantum number L, which indicates the sublevel that this electron is in. There's a quantum number m sub L, which indicates any particular orbital of the sublevel that this electron may be in. And there's a quantum number called m sub s, which indicates the spin of this particular electron. Okay, so what are the values of these 4 quantum numbers for this electron of hydrogen? So n is just the energy level that this electron is in. So n for this electron is 1. How about L? L indicates the sublevel the electron is in, and here's a little bit of memorization. You might recall when L has the value of 0, what that indicates is that that electron, if L is 0, is in an S sublevel. If L has a value of 1, it's a P sublevel. It's a value of 2, it's a D sublevel. If it's a value of 3, it's an F sublevel. Okay. So here we have an electron in the S sublevel, so the value of L must be 0. the value of m sub L, you may recall, it can vary from plus L through 0 to negative L. So here, because L is equal to 0, m sub L is 0 to 0 to 0. It's plus 0 to 0 to negative 0, which is 0. So there's really only one orbital in the s sub level in the first energy level, and this orbital will have an m sub L of 0. Okay, so how about what the value of the spin quantum number is? And so it could either be plus 1/2 or negative 1/2. And so if we draw an upward arrow like this, by convention we say that this electron is spinning in a clockwise direction. And if that's the case, then we assign a quantum number to that kind of electron of plus 1/2. If it was spinning in the opposite direction, we would say it would be negative 1/2. But it's going up, so it's plus 1/2. Okay, a Lewis dot structure. Okay, this will become more important later, but I'll teach you how to draw out a Lewis dot structure. What this is a representation for a particular element, how many electrons there are in the highest energy level of that element, in which you can sort of figure out from these notations. So the first thing in a Lewis dot structure you write is the symbol of the element, which is H. Okay, and then you ask yourself this question: how many electrons are in the highest energy level of this element? So what is the highest energy level that electrons are in hydrogen? Well, there's only one electron, and its highest energy level is the only one that's there, and so that's the first energy level. And so there's one electron in the first energy level, which is the highest energy level that electron is occupying in hydrogen. And so therefore, since there's one electron there, we write one dot, and we put this dot next to the symbol. Okay, paramagnetic or diamagnetic. So let's talk about what makes an element as paramagnetic and what makes it as diamagnetic. So first off, what paramagnetism is that it suggests, or rather, if you have an element that is paramagnetic, what that means is it'll be attracted to magnets or magnetic fields. On the other hand, if you have an element that is diamagnetic, it will not be attracted to magnets or magnetic fields. In fact, it might be slightly repelled by them. So how do you determine whether an element is paramagnetic or diamagnetic? And the way you tell is by looking at the orbital notation for the element. An element is diamagnetic when all of its orbitals, every single one that has electrons, has a pair of electrons in them. On the other hand, an element is paramagnetic when it has at least one orbital with only one electron in it. Now, it could have more than one orbital with one electron. There may be two orbitals or three orbitals, each with one electron. Doesn't matter if you only have one or more. If there's an orbital there with just one electron in it, that makes that element attracted to magnets or magnetic fields, and so it's classified as paramagnetic. So hydrogen here has one electron in the one orbital that it occupies. It's not a pair here, it's just one. Therefore, it should be attracted to magnets. The hydrogen atom, at least, should be attracted to magnets, and so it's considered to be paramagnetic. Okay, so the next element we're going to talk about is helium. And this has two electrons.